Now, students sometimes find transformers really tricky. There's this kind of electrical box that you plug stuff in, and then out of it we get a different potential difference in current.
Yep.
What are some of the approaches that you've taken that really work when you're explaining how transformers work at GCSE?
This is actually I suppose my bread and butter transformer demo. I allocate a good half lesson to it because I don't want to rush it. I certainly remember not being taught transformers terribly well when I was at school, and this was a way of demonstrating it that I was shown very early in my career that, to be honest, is so good. I've never used anything else, and every school I've gone to I've sort of tried to get the kit to do the own equivalent of it. The thing about this, I think the key is to show the pupils bit by bit exactly why a transformer is the way it is built the way it is. Most textbooks, and I suspect therefore a lot of teachers, will just present pupils with a ready-made transformer and say, look what this does. And that's fine, depending on how much explanation you give. But I think showing them how it's built up step by step is a really, really valuable way to let them see at each stage exactly why everything is the way it is. And lots of other things about transformers, like the fact that they only work with AC, or only work effectively with AC, just comes naturally out of this story, I think. So, I've got a power supply. The eagle-eyed amongst you will notice that I've already got it set to DC, and you might think that that's a mistake, but it isn't. I've then got my these beautiful large demo meters that I know, Lewis, you're a great fan of.
Yeah, I'm particularly jealous just for when you're demoing things to a whole class that everybody can see the reading and you're not having to project onto the board. But I appreciate that's just what was in this school when you arrived, wasn't it? And they're kind of something that not many schools have, but it's...
No, indeed. It is, it's great if you've got them. If not, any meter will do. You could display it on the screen. There's lots of ways of doing that, but if you've got them, excellent, use them. So I've got it set to DC volts, full scale deflection of 10 volts, no particular reason for that, just that it happens to work quite nicely. And all I've got connected, I have not got a transformer connected yet, all I've got is a single coil with, it's stamped on, it might be tricky to see, but that's 600 turns of copper wire. You'll see why I'm using 600 with this particular kit later on. So I've got it set up so that when I switch on, I just get a nice straightforward... No, I don't. Why is that not happening? That changed a little bit. Does sometimes vary a little bit, but I've got, just for the sake of a nice round number, I've got 10 volts DC feeding into this copper coil with nothing else there at all, apart from a voltmeter and a power supply. So at the moment, and I would do this in terms of teaching order, I would make sure that I've done, to my and the class's complete satisfaction, electromagnets and electromagnetic induction. So I've done my electromagnets and done coils and core and current and all that sort of thing. And I'll make sure that I've done EM induction, so I've done waving a wire around in a magnetic field showing that you get an induced EMF and so on and so on. Yeah. So and I would even recap that before even starting on this. So the class are really clear exactly what and how you can use an electric current to create a magnetic field, and how a magnetic field and motion of some sort can be used to induce an EMF and therefore
and I guess in our order of teaching we tend to do transformers at the end of this topic, so they're the things that will have been covered before this that build up on
absolutely and a transformer, when it's really well understood, I think is a beautiful example of how things that you might have studied slightly separately one after another then come together and show you how you can make something genuinely enormously useful.
I think it's just a wire that's slightly loose or something. I think when you tapped it, it went back down. So
okay, that's very peculiar.
It's got on video, and it's we're doing a bit of a demo, so that's why it's.
These things do sometimes happen. Maybe that's why it was higher up to start with.
Yeah. Anyway, so that's
okay. We'll keep.
So we've got a 10 volts.
That doesn't normally happen.
So that's 10 volts, is it?
10 volts DC going to here. Now, of course, at this point, you would point out that you would elicit from the class, hopefully, that this would be creating a magnetic field, and hopefully they'd be able to visualise the sort of fountain of magnetic field lines going around through the desk, forming complete loops, and so on and so on. If you've got one of these are terribly cheap and terribly good fun. This is called an inclinometer. A lot of suppliers make them. It's just a very, very tiny magnet mounted on a double gimbal, so it's free to rotate in 3 dimensions. And so therefore it's effectively a 3-dimensional compass. You can even take it away to one side, switch everything off, and show that it's following the Earth's magnetic field line. So that is actually grid north, and the red north pole. The red north pole is pointing towards that.
Yeah.
And just nice as an aside at this point, sometimes if the class won't get too distracted by it, to point out that the magnetic field lines at this latitude, for example, are going into the Earth at about 60, 70 degrees, as opposed to the usual two-dimensional component of it that you get with the navigation
assume that everything is kind of in the same plane as the Earth, don't we? But actually, I guess the field lines are going to go down, not just along the...
Absolutely. We're so used to seeing compasses that, of course, are constrained to only move parallel to the Earth's surface. It can be easy to forget that, of course, the field lines are actually...
I hadn't really realised that.
But anyway, if we switch this on, and hopefully we'll get back to our 10 volts.
Yeah.
Fabulous. And if you move this around nearby, you can do this with normal magnets as well. That's why these inclinometers are lovely. You can actually just show them visually the field line shape. Almost like a plotting compass, I suppose, except that you can just move it around. I'm always amazed, even classes that are sometimes quite difficult to impress. It's amazing, maybe it's the aesthetic, I'm not quite sure.
Anything with magnets.
Yeah, that's true. They always like. It's amazing how kids like that. But it's just nice to emphasise to them, help them build up the visualisation of the field lines. So just to emphasise what they hopefully will already know and be happy with at this stage, that there's a whole load of field lines coming out there. Separately, maybe switch that off. Sometimes by the way, sometimes the cores do start to get quite warm, so I'll just switch it off when it's not absolutely necessary.
And so this is nice because it's a separate circuit completely.
Absolutely.
There's no connection between the first primary and the secondary circuit.
Yeah, so separately on the desk I have set up another ideally identical meter, though of course it doesn't have to be. This one is set up to register milliamps DC, and it's on a centre zero setting. And you'll see why in a second. Yeah. And I've got connected to this an identical coil, so this is also 600 turns. And as you can see, really obviously visually, as you say, there is absolutely no electrical connection whatsoever between those two circuits, which I think is something that doesn't always come across in the traditional transformer diagram. It sometimes looks like there's more of an electrical connection than in fact there is. So literally all I've got is a single coil connected to an ammeter, and that's it. At this point, if you've got a magnet, it can be a strong one like this, it doesn't have to be, but you can wave it around nearby and just show them what, again, hopefully as a recap for them from the last lesson or the last couple of lessons, that a movement of a magnetic field near a coil induces an EMF, and because it's part of a complete circuit, therefore induces a current.
Yeah.
And so you can wave it around and they're happy with it.
And you've got just a neodymium magnet in that box.
Yeah, absolutely.
That's quite a nice way of holding it. And I guess if you're not a specialist physics teacher, although at A-level we talk about inducing an EMF, it's really, often just all called voltage or potential difference at GCSE.
Yeah, so for GCSE, check your syllabus. Some syllabuses are very fussy about potential difference, not voltage. Some syllabuses are, some specifications are entirely free and easy about it. Just go with whatever your specification says. Below A level, saying generating a voltage is not something that I personally lie awake at night worrying about.
No.
Though at A level, I would be more careful about saying inducing an EMF, for example.
Okay.
So you've reminded them that a movement of a magnetic field near a coil of wire can generate a voltage, or whatever phrase your syllabus is going to be most happy with. And the thing at this point to ask them is, does this coil know or care whether the magnetic field that's moving around near it is coming from a permanent magnet or an electromagnet? And if the pupils have understood what's going on so far, they should realise that a magnetic field is a magnetic field in those terms. So therefore, if I switch this on, generate my magnetic field, this now in magnetic field terms is not really any different to the permanent magnet. So if I move this around near the coil, I should get, it's not a huge effect, but I should get some clear induced EMFs.
Yeah, there's definitely movement on that dial.
There's definitely some current in that circuit, and it's going one way and then the other, as you'd expect. And if I turn the coil round, the deflections are reversed. So all the things that hopefully the class would be quite happy with at that point. This should not be surprising yet. So at this point, it's wandering again, isn't it? At this point, you say, okay, that's fine. How could I make? But at this point, you could say, I'm using, using quite a lot of energy here. It's a bad phrase, but you know what I mean.
Yeah.
This is getting quite warm, and all I'm getting is a few little sort of, fractions of a milliamps, not very effective. How could I make it more effective? Another nice bit of revision. Hopefully, at some point, that someone will tell you that you could put a soft iron core in here to make the field stronger, and usually in these kits, which are often quite old, you can buy newer versions. Most schools have just got one that they've had for ages, sometimes sitting dusty in the back of a cupboard. At this point, you can get your soft iron core out, put it in, And you can just, beg your pardon. Before I do that, I say, right, instead of me physically moving it,
yes,
as I was before, instead of me physically moving it to get an induced EMF, if I just put it stationary there, I'm still applying a voltage to what in a moment we're going to call the primary coil, but I'm not getting anything out, and hopefully you can then encourage the class to appreciate that that's because there's no motion. The field is static and there's no physical motion, therefore there's no, in GCSE terms, field lines cutting through these wires, therefore there's nothing being induced. At this point, if you say, if I switch off, and you might need to help the class at this point to appreciate that when you switch off, that magnetic field collapses. You say that if that magnetic field is then made to collapse, would we get something out? And at that point, the class might spot it and might realise what's going to happen. They might not, but you can just show them. So I'm now going to switch off. The field's going to collapse, and we are going to get a deflection on the ammeter. It's not very big, but it is there.
Yeah.
And that's because the field's collapsing inwards, and any motion of a field line, any motion of any field lines through a coil will induce something.
So I suppose what you could do is turn that on and off 50 times a second very quickly.
You're jumping ahead at that point, as sometimes the pupils do.
Yeah.
And at this point, you can just try switching it on and off a few times, noticing that that is either on or off. And what happens is we get a flicker when we switch on, but it goes back to 0. Even though this is on, it's gone back to 0 because this field is now stationary. And then when we switch off, we get a deflection in the opposite direction. So it was a
very
flicker.
small.
It is very small, but it is definitely there. So switch on, flicker one way, and then back to 0. Switch off, flicker the other way, and then back to 0. And hopefully they can then, this is the new information for them, the idea of the field growing when it switches on and then staying stationary, and then collapsing when it switches off, will enable them to see that even though there's no physical movement like there was before, we are still getting induction effects.
Yeah.
So at that point you say, fine, but those flickers are very small, can be difficult for kids to see. Could we make those flickers any bigger? And that's where hopefully you elicit the idea from the class of a soft iron core. So if I stick a soft iron core in my coil that's connected to the power supply, that will now make the same thing will happen to the field, more or less, but it will now be much, much stronger, so there'll be more, in GCSE terms, more field lines cutting through the secondary coil per second, so we should get a noticeably bigger deflection at this point.
Yeah,
definitely on, bigger. And still back to 0. Keep emphasising that every time it's the voltage is not changing, you don't get any induction effects. That's a really important thing for them to get. And then when you switch off, again, a flicker in the other direction, and that's that.
Yeah.
And you say that's lovely. Would it make any difference if I put the coil here? This sometimes gives them a pause for thought. Some kids will go yes because of some sort of symmetry. Perhaps they might be thinking intuitively. Some kids think no, the core has to be in there. Actually, it doesn't matter. You get, because of the symmetry, for a simple way of explaining it, because of the symmetry, there's actually no difference. So if you say, right, we get putting a core there helps, putting a core out there helps, surely putting a core in both would help. And usually by this point, you've hopefully got the kids sort of, shouting out their suggestions or making their suggestions. And at this point, you whip out, usually what comes with this kit is the beginnings of a transformer core. So you can say, right, I've got a core for both now. Isn't that nice?
And even though it's made out of metal and iron is a conductor, it's insulated from those two circuits.
Yes, and it's all sometimes worth just emphasising to pupils that on the inside here, this is just all insulated. This is some old.
It's like Bakelite.
I was going to say it looks proper like, just to show how old some of these things are. Modern ones will be plastic, I'm sure, but there is no electrical connection there at all. Now, when you switch on, we get an even bigger effect because we've given both of the coils a core. So now, when we switch on.
I think that's a pretty.
I think the meter's fallen asleep. They do that.
I think it's pretty straightforward, isn't it? That is.
So huge deflection now when you switch on, and still back to 0. I'm never afraid to emphasise that over and over again till the point where the kids get bored with it, because that means they know it.
They do.
And then exactly the same when you switch off, but much greater. And hopefully by now the narrative is building up quite nicely. What you can also do at this point is emphasise to them that there is a magnetic field here. There might be no electrical current that we're going to tell them about yet flowing in the core, but there is a magnetic field. You can get your inclinometer back out, and at the moment there's a little bit of deflection because of it being this magnet being attracted to the iron, but there's not really anything terribly noticeable going on there. Whereas if you do that, it gets terribly excited, and you can actually follow the field lines.
I've never seen it done like that before. That's
and
nice.
Help them visualize that the field lines are not only going through the core as you would expect, but they have to go through the air as well, and you can visualize the sort of curvature of them, which is a really valuable thing to have a good, clear mental picture of. So we're all doing quite nicely. At this point, depending on how much detail you want to go into, depending on the class, you could then go into a little bit of detail about reluctance and things like that, and talk about air not being a very good conductor of magnetic field lines. You might want to think carefully about exactly what terminology you use. You might end up going down a bit of a conversational rabbit hole with the class. But if you just say, okay, we've made a much bigger flicker, which is lovely. Could we make it even bigger? Well, the magnetic field lines, you could say, flowing or can flow easily. Flowing is always a slightly... can be problematic when you talk about magnetic field lines, because they don't actually flow, but it's so easy to think of them in a lot of ways as if they do. So the magnetic field lines flow, if you're happy with that phrase, through the iron quite nicely, because iron's a magnetic material. They don't flow through the air very easily, so therefore there is some magnetic energy. Again, you might want to be careful about your terminology there. There is some of the effect, keep it vague perhaps, some of the effect is being lost as a result of this air gap. And the equivalent of a good conductor in magnetic terms is just more iron. So if I put some iron on there, I forgot I had this switched on.
Because I guess you can...
Make sure you switch it off, because otherwise they'll get distracted by the sudden effect there. So yes, you make sure you switch off at that point. You talk about the air gap, and then you say, so if I take this one that I was using as a core and use it to bridge the gap, then there's now no, apart from a tiny, tiny air gap, there's no real air for it to flow through. It's all flowing through iron, nice magnetic material. Should work quite nicely. So at that point, you switch on. At this point, we should probably get too much deflection for the meter.
So it's definitely
now going off the top. So at that point, I would probably just say, I'm going to make this meter 1,000 times less sensitive. So I'm going to change it from milliamps to amps. So although that looks the same, hold in the back of your head, I would say to the class, that this is now 1,000 times less sensitive than it was before. And of course, so now we go back to what look like small deflections, but you need to remember that in absolute terms, it's much, much bigger than it was. Just to make it a bit clearer. Another nice thing you can do at this point is to just show that the by the way, just from a teaching point of view, it's worth knowing that although this is nice soft iron, it does have a certain coercivity, so it will retain a little bit of magnetism. So sometimes it won't just come off really nicely like that, because of course it's only sitting there. When you, what I would then show to a class is that when I magnetize it, when I switch on and this all gets magnetized, you can actually pick the whole thing up, even though it's really heavy. Just to emphasize that it really is being magnetized.
And the soft iron is something that is soft because it just becomes magnetized and demagnetized very quickly or relatively easily.
Without a huge amount of effort. When you switch off, it's good for the pupils to appreciate, it's helpful for pupils to appreciate that it instantly gets demagnetized because of the soft iron effects you've been talking about. In reality, you don't necessarily need to go into this, but in reality it's worth knowing that it does actually retain a little bit. I did have to pull there. You might just want to, just for sort of showmanship purposes, just to, so you don't get into that particular rabbit hole, just sort of ease it off at an angle, and then so you can show, nice and magnetized, switch off, and then just ease it. Sometimes you do have to be careful.
And I think it really depends on the equipment that you've got in your school.
Yeah, absolutely.
And I think, again, at GCSE, you know, we can see that there's different layers to that core, but at GCSE we tend to talk about 100% efficient transformers, and we don't need to go into eddy currents necessarily or why it's laminated. I think some students will
It depends on the syllabus. Certainly at A level you would. A lot of...
at A level you talk about it, at GCSE you might
GCSE
not.
less so, I suppose,
But again,
I often cover it anyway. And one nice thing you can do is just have your hand on the power button and just show them, look, it's not magnetized, it is magnetized, which is quite nice, just to emphasize the point.
And you're still using DC at the moment?
And I'm still using DC at this point, and we're just getting flickers when we switch on and flickers when we switch off, nothing in between. So at this point, encourage the pupils mentally to take a bit of a step back and go, what have we actually achieved? And the answer is, not a lot. All we've got is a very complex way of turning a constant voltage, which is of course costing you in energy terms, or if not in money terms. We've got a constant input, and all we're getting is a flicker when we switch on and a flicker when we switch off. So we haven't got, you could be forgiven at this point, I would tell a class, for thinking that all I've got is a very complicated way of doing something that's not terribly useful, and I wouldn't particularly argue with that. So to make it useful, what we need to do is, well, the problem is, you would say to a class, you're just getting a flicker when you switch on and a flicker when you switch off. Now you can just therefore stand here and just go on, off, and you get a sort of consistent output.
Yeah.
And at this point, hopefully someone in the class will have a vague recollection of you having done DC and AC. So at this point, they would then say, oh, couldn't you just connect it to AC? And you say, yes, absolutely. And even though you could have done that all along, you've now then, hopefully, as the way this is built up, this has now enabled them to remember really quite clearly that transformers are not very effective with DC, which is a question that often comes up in exams. And having shown them this in this level of detail, hopefully makes that go in rather than just remembering it as a strap line that they don't necessarily understand. So at this point, you say, fine, I'm going to change over to AC. And I therefore need to change this meter because this meter on DC will just...
so again, that really depends on the kind of meter that you've got at your school.
Absolutely.
And if
some meters will adjust for it automatically.
Multimeters might perhaps work better than a normal voltmeter that you
possibly. Analog always helps though so much with pupils, I find.
Yeah, no, definitely.
Also, you'll probably find that the power supply, even though it was giving 10 volts out of the DC outputs, you'll probably find because of all sorts of complex reasons, it might not give exactly 10 volts, so you'd have to watch and do a bit of adjustment perhaps. I also need to change this meter to be ready for AC and also to make it completely symmetrical now. I'm going to change that one to volts as well. This is the only thing where I'm slightly, I just think it's slightly imperfect because you've kept this one on volts all the way along, you've had this one on amps, and then now you're changing it to volts, and that's a mental switch that might be problematic for pupils. You just need to sort of think about that one. I just know from experience with this kit that if I'd had it on volts or millivolts to start with, I just don't get anything noticeable, so I have to have it on milliamps with this particular kit, and it means I have to do that slight shift, which is, it's not ideal, but it doesn't seem to cause any huge problems really.
Yeah.
So at this point, I would point out to the pupils, also change the display.
Here we go. I love
change
that.
the display, and now to point out to the pupils that these meters are completely are displaying identically now.
Yeah.
AC volts to 10, AC volts to 10. So you can now make a fair comparison, completely fair comparison between the two.
Yeah.
At this point, if you switch on, I think it tends to go over 10 amps a little bit, 10 volts a little bit. So back it off just a little bit. So just back to 10 volts where we were. And now what we've got is our transformer working almost as a normal transformer.
Yeah.
Obviously we know it's 600 turns, so it's 1-to-1, but the pupils won't be worried about that too much yet. And we're now getting 10 volts in and not quite 10 volts out, which is a lovely way of emphasising this whole transformers being, as far as we're concerned at GCSE, 100% efficient. It's never quite perfect, but it's jolly close, and that will hopefully make a class happy that assumption is not completely outlandish.
Yeah.
And at this point, you can say, great, I don't have to switch it on, switch it off. I'm getting a consistent input. Okay, it's AC, but it's a consistent input. Emphasize to them that it's changing direction. So at this point, to tell the story, the magnetic field, the current here is going one way, then the other, one way, then the other. That's generating a magnetic field in one direction, which then collapses and then generates in the other direction, and then one.
Yeah.
Bit of hand waving, which is alternately magnetizing this one way and then demagnetizing it and magnetizing it the other way, and so on and so on and so on, 50 times a second. And that means that the magnetic field lines are constantly cutting through, in GCSE terms, this coil one way or the other, 50 times a second, which is why we're getting a consistent AC output. At this point, just worth checking that the class are completely happy with exactly what's going on, what they're seeing, and why it's happening. A nice thing at this point is also to muck about with the yoke on the core and point out that it was more or less impossible to pull off on DC. It was incredibly strongly magnetized. But with this one on AC, because it's only spending some of its time magnetized and some of its time demagnetized, you can actually take it off. And actually, if you pull it off slowly, you actually get some transformer chatter, some transformer hum, which anyone with perfect pitch might be able to tell you is about 50 hertz, which is rather nice. People like that. And also, it's quite easy to pull off. And also, a lovely thing when you take the yoke off, you're now going back to your air gap, and you notice that your efficiency drops like a stone. It's gone from being 90-something% efficient to about 40% efficient.
And I think actually using the kind of 0 to 10 scale, it's just dropped completely.
I think it's just switched itself
off. I think again that shows, even though you've got the numbers there, it's really easy for students to kind of calculate that efficiency as either a percentage or a fraction.
Yeah, which is one of the reasons that I start with 10 volts.
Yeah,
because it makes the percentages almost intuitive.
And is that getting warm? Because actually my camera's getting warm at the moment. I can see there's a warning light flashing on saying my camera's getting hot from filming.
Actually, this is getting quite warm, so I'll probably switch it off at this point. Now you're almost home and dry. At this point, you can still point out to the class that all we've managed to, if you've got a cynical point of view, you might say that all we've got is an incredibly complex way of turning 10 volts into not quite 10 volts. So at this point, you could argue, still, why are we bothering with this? And at this point you go, well, you remember that we had 600 turns and 600 turns, so it was a symmetrical setup. What's going to happen, and usually with this kit you have physically identical coils, but with different numbers of turns. So I'm now going to turn it into, and I always do it deliberately this way, I'm now going to turn swap the secondary coil to 300 turns.
So it starts at 600 on the primary. 600
to start with. I'm now going to go to 600 primary, 300 secondary.
Yeah.
And just move it right over. So we've just changed over, having built up the idea of how it's worked, we've now changed over to 600 turns, 300 turns, primary, secondary. So in our heads, this is now a step-down transformer. They probably wouldn't be using that phrase with the pupils yet. They've seen with 600, 10 volts AC in, almost 10 volts AC out, and now you ask them to predict with 600, 300, 10 volts AC in, what would you expect out? And just intuitively, they'll probably say about 5 volts, and they're right. It's exactly what you'd expect, and it's exactly what happens, which is great. So now at this point, you can say, now finally, this was all worth it, because now we can do something useful. We can now take any fixed AC power supply, and with the right choice of numbers of turns, we can now turn any fixed AC power supply into any other amount of AC volts that we want. And this, of course, is exactly what happens in something that's very close to their heart, which is, of course, their phone chargers. Their phone chargers can only have a fixed 230 volts input, yet the battery and the circuitry in your phone is designed to work on about, I think it's about 5 volts or thereabouts. 230 volts straight into a circuit designed for 5 volts is a really bad recipe. So therefore, what's in your mobile phone charger, or what usually gets called the brick, if you've still got a laptop charger like that, is basically a transformer, which is why they're fairly heavy, because you need an iron core. And so lots of things that they've noticed in their everyday life are hopefully now starting to become clear. And they're all nice and happy with that. And at this point, you can pause. You can give them a diagram for their notes. You can talk about the numbers involved. You can bring out the equation if you want.
But I guess you can also swap around I guess you can just unplug that and flick it around, can't you?
You can. And sometimes a pupil will say, what about if? Which is, of course, a very good question. I would sometimes pause, let them do a bit of writing, because my voice will need a rest, if nothing else at that point. And then either someone will suggest, or you can propose it, say, right, you take the 600, 300 input output, or primary, secondary, if you're using that terminology by now, turn the whole thing around, make sure it's off, reconnect, 10 volts AC in.
So if you're putting 10 in,
what's going to happen now? And at this point, it's interesting, lower ability groups will be quite happy with 10 in, 20 out. But really good physics thinkers will think, that mathematically is what should happen, but I'm not happy with the physics of that, because at the back of their head they've hopefully got a good understanding of conservation of energy. So it's interesting, it's really fascinating to see what a group will give you at that point, whether they're happy with saying 20 volts out, or whether they're
because it almost feels like it's 200% efficient then, doesn't it?
Exactly. So at this point you switch on, and it goes way over the top, and you can change range and show that it is actually basically 18 volts out. And at that point, hopefully, if you've got a class that have been taught well and are thinking about these things actively, someone somewhere will start to have a little niggle in the back of their head saying, you're getting something for nothing there. If you time it right, you can get the bell to ring at that exact point and then say, right, I want an explanation of that for the next lesson.
If anybody could plan their lesson that well, they get the bell to ring just when these questions come up.
If you've been keeping an eye on the clock, it's amazing what you can do once you've got a bit of experience. So a cliffhanger at that point. Have I actually just managed to break the law of conservation of energy that physics has been happy with for a century and a half? Have I got something that can solve the energy crisis? You can ham it up a little bit. And of course you haven't, and then sooner or later, you usually will have to tell them that actually all you're seeing here is half the story. You're only seeing the volts.
Yeah.
A good pupil might be able to say, what about the amps? What are we not seeing here? And at that point, you can then just explain to them that anything you gain on the volts, you lose on the amps, to put it in very sort of colloquial
But I guess
terms.
if you're talking about electrical power and how power is current times voltage or current times potential difference, power in is power out, pretty much for an efficient transformer, and therefore if you double one, you halve the other. So it's this.
Yeah, exactly. And so from this point on, it should be a relatively short step mathematically to put something like VP IP equals VSIS or something like whatever your specification does. And it should then be reasonably obvious why that has to be true. And they'll have seen something that they can link it to that makes it all clear. So after all that, it does take a while. And it's quite laborious, and you've got to it's got to be a class that can cope with that level of narrative. With classes that struggle with attention, you might want to break it down on a worksheet, get them to do some writing in between. That's sort of your own teaching professional judgment. But one way or another, if you build it up this way, you still end up with the same classic transformer setup, and they end up with the same diagram in their notes or whatever. But what you don't end up with is this being some sort of abstract machine where they're not entirely sure exactly where currents are flowing, what they're flowing, which direction they're flowing in, what's going on in the core, why you need a core in the first place. All of those questions that I think, if you just present pupils with, this is a transformer, this is how it works, I think there's an awful lot. I think the understanding that most people are likely to get from that is going to be is in danger of being quite superficial. Whereas this, by the end of it, hopefully they will have a genuinely deeper understanding of exactly what a transformer is, why it does what it does, why it can't do certain things, like act effectively with DC, why everything needs to be made the way it is, and so on. Their understanding is so much better.
Awesome. Thank you.